So let me just get everything here sort of set up here. I'm just actually in the process of just fiddling around with things, so please don't mind with me. This is mostly a test stream for me to figure out what small things I need to do. I also must note that this is right now streaming technically in at least a few places, so keep in mind that I might not be able to see your comment if I can't see you in one of the chats I'm looking at. So in particular, I'm looking on YouTube, so just keep that in mind. So I'm just over on the PageWizard Games Learning and Entertainment channel. So I'm just going to actually go over there and just make sure I have that open. Oh, I hear myself. I hear myself. So I'll be keeping an eye on that. I'm just getting things prepped here. Note that I would, when I do this normally, I would have a prep screen, just a splash screen, just to make sure that everything's all ready to go. I just like to be transparent with things. And I've been trying to get a lot of equipment together, so that hence why the delay on some of my videos. So I'm really looking forward to some of the things I'm going to be getting very soon to start up the new series. So if you're watching this and you're like, what the heck is going on here? What I'm going to be doing is I'm going to be doing the Big O Bootcamp. This content I originally did in a live stream back in fall, but I wanted to redo that content with the newer equipment with the higher quality video. So hopefully you like that. I'm just having myself a good time here. Let me just getting this out. Just gonna see what it's looking like on. It's worth noting that the we also do have a. Well, I also have a live. Oop, that's a little loud. I'm just looking at things at the moment. I apologize if you hear any strange blips. My microphone's right here. Sometimes I move my arms around a lot, so I tend to do a lot of that kind of stuff. We're gonna have a good time here. Just want to find the page, our current page. I don't use my Twitch as much as I would like to use it. I would plan to use that a little bit more. Let me see, Stream Manager. Okay. Okay, I can hear myself. That's good. Okay, so I have the Twitch chat open. That I'll take a look at that. And then I'm going to do this. Just getting things together here, so please don't mind me. Also, if I'm looking down here to break the illusion that everything in here is self-contained, there's a computer right about here. So what we're going to be doing is, so hopefully without hearing too many audio things elsewhere, I'm going to be doing this all recorded in advance, and I'm also doing this streamed. So what you're watching right now is going to be the raw footage for what I'm going to be editing up and later you'll see on the YouTube channel. So if you're watching, say, this in the future, I'm probably going to unlist this stream after, possibly. I might keep it up, who knows. If you maybe are a Patreon supporter or on Subscribestar, I'll probably keep a link to this so you can see this in the future. Do take a look at the links in the description. I also do have a Patreon and Subscribestar to support the content I'm producing here. So if you're watching this, you're like, damn, what the heck do you do here? Well, I create free or accessible computer science educational content, but I'm also doing things like I'm working on a computer game. I'm also working on some entertainment content that's going to be on the channel. But primarily this channel is going to have educational content. So if you want to learn about computer science, algorithms, we're going to do some more applied stuff actually sometime in the near future. We're going to do some programming tutorials. So I'll be doing that with everybody. That's at least the plan. I also have a new series I'm going to be doing sometime pretty soon that will involve graph theoretic algorithms. So I'm pretty excited about that. Just got to send out one more link just in case. Okay. So, okay. So this is sort of the fun with this stream, is that you get to see everything that I'm doing behind the scenes too. So we're going to have a little bit of fun with this. So I'm going to be doing a bunch of examples, but also we'll be treating it sort of like watching a show too. So it'll be somewhat more leisurely between things, but you also get to see all my rough cuts. So which should be a little bit of fun too. This is my first time using the new equipment here. You might notice this actually should hopefully be of a much better quality than it was in the past. So it's also worth noting, one other thing, is that that right now I'm only using one board. It's because I'm actually getting some more equipment to move my camera around. I've got a motorized dolly that I'm going to be using for the videos. So this I've used from the funds that I've gotten on Patreon to support creating the educational content I do. This will be done, so I hopefully will be using that in my new series that I'm doing. That will allow me to make use of both boards, but also keep the content in camera view roughly about where you see things here. So the video quality should hopefully be substantially better, and it won't be just one still shot, which I'm really excited about. The only fun of that is I'm going to have to make sure I don't lose the camera by making it fall off the edge or something, because it's a motorized dolly. We're gonna have a good time here. That's all I'm saying. So I got some demonstrations and a few things that we're going to be doing during the live stream. So this, you could treat this like I'm just having a fun test stream with you, but at the same time, I'm going to be creating some content here that you'll see on the channel. If, say, you come here in the future within the next week, you'll see a bunch of new videos popping out, which content from this live stream. We're going to have ourselves a good time, as I said. I just want to check on things on Twitch. Yeah, nothing's going on Twitch. Okay, good. So also, it's worth noting, if you have any questions, just leave them in the YouTube chat. So if you're watching this on YouTube, just feel free to use the chat. I am here. I've got it right there. So I'll be periodically checking that in between my examples. I just want to get my OB. I got my setup here. I'm just going to downsize that a little bit so I can see everybody's doing. Hopefully the audio is okay. Okay. So we're going to get started here shortly. By the way, hopefully you're having a wonderful day. I've been missing being in front of the camera here and enjoying things with everybody. So hopefully you're enjoying this. So if, say, for example, if you're a student that's learning programming or computer science right now, or you're in a class that involves analysis of algorithms, you're going to find a lot of the content I'm going to be talking about in this stream very helpful, especially if you're learning and doing practice and exercises involving big O notation. Because what we're going to be doing today is I'm going to be doing a bunch of examples involving proving claims with big O notation. So I'll be talking a lot about that kind of stuff. I'll be showing you a couple of the standard tricks involving polynomials. And I'll be winding this thing up with a more sophisticated example showing you that the harmonic, so the finite harmonic series, I believe it's the nth harmonic number is logarithmic in terms of big O notation. So we're going to have ourselves a good time with that. I'm just going to check one more time that things are in order. I'm just going to send out one more link. Somebody was asking me for a link to the Twitch. I'll put a link in the Twitch as well. Let's see here. Since I have my screen dimmed, it makes things a lot harder to see. Just getting links. little loud. Because my microphone's a little bit too, I know. That's bad. That's bad. My apologies. That was my bad. I leaned in too forward a little too much there. My apologies, headphone users. I am just figuring things out here. As I said, this is a test live stream. I just want to make sure I don't. Okay. No tilting forward too much. That is not a good idea. I'm just gonna make sure my microphone doesn't do too many fun things like that. Okay, so gotta make sure I don't rub this suit across. Oh, okay. I'm going to just do one small thing here. I'm just going to max out the gain. I think that might help a little bit. And I'm also going to move my microphone up just a tad more. Okay. This might help a little bit. Okay. Okay, okay, that's a bit better. That's a bit better. So now I can tilt forward and it's not going to kill everybody. Okay. Okay, good. Thank you. Yeah, so, like I said, we're figuring things out here, so I apologize in advance. If you're wearing headphones, holy jeez Louise, that would be brutal. So, let's see here. We're gonna have ourselves a good time. Let me see here. Okay, going to close things here. Let's get started here. So hopefully, I just want to make sure I do the tie test. If you're wondering why I clip my microphone here as opposed to up here, is because I do a lot of looking down, up and down a lot, and I find if I have it clipped up here, when I turn my head like this, the volume gets much louder. Because I don't stay in one stationary spot. As you can probably guess, I move my arms around a lot. So it's better to keep me roughly in the middle of me. That's why I normally do it this way. I find it works pretty well. Just if I don't position this in the right spot, it might just dip down a little too much, and that isn't good. So hopefully the volume is okay. It's not too quiet. Just keep in mind that after, when you watch the videos, like say if you watch any of the content from this after, I'll be editing it and improving the volume levels. So hopefully you can still hear everything just fine. Normally I attach it to the camcorder, but I found that the filtering for the audio wasn't working as cleanly as I wanted it to. Let's see here. Okay. Just gotta. Somebody's telling me that it sounds crystal clear. Okay, there we go. Okay, good. So, we're going to get started here. I'm going to pretend that I'm coming in from over there, which will be a lot more fun here. I'm going to put my hat on. Just going to get this on. We're going to get started. We're just having a little bit of fun here. We're going to probably do another one of these when I get the more of this camera equipment in. But I plan to do more live streams on the channel, so that'll include some more tutorials. So this is just more of me wanting to do something fun with you guys, but at the same time also get some educational content out there, because I've been sort of in a drought for the last couple months because of preparing all this equipment. Okay, let's get started. 3, 2, 1. Here it comes. Hello, everybody. I hope everyone's having a wonderful day. So today we're going to be doing the Big O Bootcamp. So you might ask, Dan, what does that mean? Okay, so I should back up one moment and maybe introduce myself. My name is Dr. Daniel Page. I'm a theoretical computer scientist. You can just call me Dan or Daniel. And we're going to have a good time today. So we're going to be talking about Big O notation. Now you might naturally ask, well, what does that mean? Well, we're going to talk all about that. We're going to talk about what the definition of Big O is. We're going to see some examples of how we prove Big O claims based on that definition. In addition, we're also going to be looking at how we can kind of take some of the ideas that I'm going to show you and almost give you a bit of a basic toolbox for proving Big O claims. So I'll be showing you at least one technique of this sort, and we'll see a little bit more of an advanced example later on. So I hope you're excited. I am here. So first, for those that are familiar with Big O notation, you can sit back for maybe about a minute. I'm going to explain a little bit of what we're going to be talking about, what this is. So Big O notation is a type of asymptotic notation. Now, that sounds like a lot at first, but I want to put this bootcamp or video, this series, in context. So oftentimes when people do things with Big O, it's normally done within the context of analysis of algorithms. So what exactly is an algorithm? An algorithm is an unambiguous step-by-step procedure that takes in input and produces output. So that's at least the definition that I tend to use without getting too overly formal. Now, when it comes down to designing and analyzing algorithms, there's sort of like a set of steps that comes up. It sort of looks like this. So it's like a first step where so imagine you have this great imagination, you come up with this algorithm, and you're trying to solve a problem. And each one of these problems can be encoded or represented with an exact specification, and that specification has input, and you're looking for the correct output. So you present an algorithm that's going to take one of these inputs from the problem and produce output, and if it's correct, it'll always produce correct output. So what we're going to do is I'm going to imagine you give me one of these. So the first step, I'm just going to assume that you present an algorithm. I must stress that this algorithm may be correct and may not be. The point is it's just some algorithm. Now, in the purview of this series, I'm going to assume that you have taken this algorithm and you have some way that you want to analyze it. So we're going to decide on a type of analysis. So in an analysis of algorithms course, this normally is worst case analysis, best case analysis, average case analysis. This is some type of analysis here. Now, it's worth noting that when we do our analysis, we usually use a model of computation to decide how we're going to do things like counting instructions and other things like that. I'm not going to worry so much about that here. Because in the third step, that's where you would do all that work. So in the third step, what you would do is you would derive a complexity function. So you derive a complexity function. So what does this mean? It just simply means that I count up the total number of operations, or I determine the order for which the number of operations or primitive operations occur based on this analysis given a computational model. In the context of algorithms, normally this is the RAM model or some version of that. It doesn't have to be, but that's the more common one. If you wonder what I mean, it's called RAM, or Random Access Model. So the random access machine model. I'm getting really excited, as you can tell. So, once you're at this step, what you normally like to do, because I would like some way of describing the complexity function with respect to something called the input size. And I want to do this and kind of collect a nugget, like just something that represents all of those inputs for every one of the instances for the problem that I can give to my algorithm. This nugget is the asymptotic notation. So before you get to step 4, you're going to compute the complexity of the algorithm. So complexity, in the purposes of this discussion, is within the idea that I want to determine the computational resources that algorithm's going to need. So this might be memory or space. This might be time. Most commonly it's time. So you compute the complexity of the algorithm. Now, the final step, this is the one, or I just want a quick question. When people thought about algorithm, did you ever think this was going to be implemented for a machine? Excellent question. Excellent question. So, the great thing is that you can develop algorithms for a given machine. So, one specific machine in mind. However, what we would like to do is we would like to come up with an algorithm that can work we want to isolate it from a machine so it isn't dependent on the machine. So for example, I can give you an algorithm for factoring numbers. It doesn't matter what the machine looks like. That's the power behind what an algorithm is that I just follow the process of the algorithm. It still gets me to the end result regardless of how the underlying machine operates. That's the mathematical beauty of what an algorithm provides for you, at least from a utility standpoint. This is why we oftentimes pick models of computation to represent when we represent those operations. So, for example, the RAM model is very much like a type of mathematical assembly of sorts. So, if you're looking for some sort of comparison to a tangible computer, think of something like assembly, and you can oftentimes think of the RAM model sort of like a very primitive type of assembly. But there's other versions of this model that do exist that involve reading words and the lengths of the words or some constant and bound the size. Like I said, this gets very technical. But if you want to go back historically, people developed all sorts of calculating machines back centuries ago. But the point and power of an algorithm is that we don't have to tether it down to a single machine. It's just a mathematical concept that we can apply given any machine that's capable of performing the operations at hand. So this doesn't have to be a tangible computer. It could be your friend. It could be your friend Billy over here, or Sally, or something like that. It doesn't have to be. I can instruct Billy or Sally to perform the operations of the algorithm. That's kind of sweet, awesome. I like answering these kind of questions. So imagine I give you one of these algorithms, and I get to a step where I get one of these complexity functions. I compute the complexity, which is just the resources that algorithm is going to require. And then what I want to do is I want to determine the asymptotic behavior. Determine the asymptotic behavior of the complexity function. So what do I mean by that? Asymptotic, think as the input grows, as it tends to get large. So I would like to determine this so-called asymptotic behavior. Why would I care about when it gets big? It's because, remember, when I talk about a problem that the algorithm is going to solve, what that means is that I also have to consider instances that are really, really, really big. So big that you couldn't imagine them. Because every problem instance of a given problem has some fixed size, but that size could be arbitrarily big. So oftentimes when computer science students or computer scientists or those that are practitioners pick up big O notation. They often look at it within step 4. So I'm not going to worry about steps 1, 2, 3, or this step right here. I just only care about step 4. So I'm going to assume that you give me what is called a complexity function, or some people call it a growth function, which I'm going to define next. So a typical activity that goes on in computing, especially when you're interested in algorithms, is this process. When you come up with an algorithm, you want to perform some type of analysis. It doesn't have to look exactly like this, but very often it fits this form. So let's talk a little bit about where things go from here. Okay. First, hopefully you're liking this little cute turtle. That turtle might fall down at some point. I like this bird. It's very cute. So, just want to pin down a couple of things, just because I said them, but I didn't write anything down. So, for our purposes, you can think of complexity as the amount of computational resources an algorithm uses. I'm going to abbreviate algorithms with alg. So that's at least the working definition I'm going to use for complexity. You thought it was Yoda? Yeah, it's just a little turtle there. It's very cute. Yeah, no, it's very cute. I know, just green. I think it's just missing the ears. Then you probably could pull this off quite well. So the point is, by some point, you would have encoded some information that represents the complexity. And we get a complexity function. So there's that thing I talked about, this complexity or growth function. So as I suggested earlier, when you talk about asymptotic behavior, you're talking about basically its growth rate. That's the other name that people call this. Instead of asymptotics, they'll call it growth rates. So what's a complexity function? Now, when you think about an algorithm, how many operations does an algorithm have to perform at least? So assume I give you, say, a recipe to bake a cake. The cake has some step-by-step procedure you follow, right? To bake the cake. How many operations, if you want to think about, just try to imagine, say, pulling out utensils, stirring a bowl. All these as different kinds of operations your algorithm would require to perform to bake the cake. What exactly would be the minimum number of operations your algorithm would have to perform? Like 1 operation, 2 operations? Like, think more generally. Like, any kind of interesting algorithm will have to perform at least 1 operation. Well, namely, there's at least one thing you can think of. The operation to conclude doing the algorithm. Whether this be outputting an answer, some instruction to say, we're going to stop. Normally, algorithms will have at least 1 operation. However, there is always the possibility of, now this is going to blow your mind. It's kind of weird. The concept of an empty program. So, I mean, there's an algorithm that has 0 instructions. This is sometimes called an empty program. And that technically could have 0 instructions, but that's not a very interesting program. So what I'm going to do is I'm going to define my definition of a complexity function to include this so-called empty program, because it makes it a little easier to work with some of the functions I'm going to be presenting to you, because I don't want to present too many concepts all together. I just want to kind of keep things simple. However, very often when I define a complexity function, I'll assume that the number of operations is always going to be positive. Why? Because there's at least one operation that's going to occur for any non-trivial algorithm. Non-trivial meaning not just the empty program. So, for the purposes of this bootcamp, and a lot of people will define it this way too. So I'm going to define a function to have it where I put in a positive number, and it's going to spit out to me some number that is either 0 or up. And I'm going to assume that is just a real number. So we're going to call it a function f on the domain of positive integers. So these are numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9. You're counting numbers. It doesn't include 0 because it's positive. Positive integers to non-negative. Non-negative meaning what? Not 0. Not 0. To non-negative real numbers. And if you want to get technical, this is what you would write down as its functional notation or the mapping notation here. You'd say that f, this is the name of the function, and this is the set of all positive integers. So I'm going to put into this function some positive integer, and it's going to spit out a real number. And the real number is either going to be 0 or up. It's going to be positive. It could be 0. I'm just going to be a little bit flexible with my definition of a complexity function. So hopefully this makes sense. So if you're not familiar with a function, I like to think of it like a machine. So imagine you have some weird machine that I don't know what the function does. I'll call it f. And it takes in some input. And keep in mind, it can have multiple inputs, but for our purposes, ours only has one. So it has input. So I put in an integer, n. So it's a positive integer. I put it in the machine. F does something, and it spits out f of n. So this is called f of n. This is the output of the function. So what we're going to be considering, or we want to look at the behavior, the asymptotic behavior of complexity functions in relation to other well-known functions. Now, if you want to get technical, all the functions that we're going to really care about are the ones that are so-called asymptotically non-negative. So that just means as the input tends to get big, they're always going to be non-negative. That means there's going to be some point for which it's always going to be a number that's going to spit out of this machine that's going to be not a negative number. It's always going to be 0 or up, or it's just going to be positive. One of the two. Okay, so hopefully my definitions here is pretty clear. Now, you might ask, Dan, where else can we use this idea of a complexity function or growth function? Well, like I said, you can capture the running time of an algorithm using this, given some analysis. But it can also be something like if I wanted to count up the number of objects that have a certain property. So for example, if I wanted to ask you, if I give you two lists of numbers and I wanted to know the number of ways I compare those two lists of numbers, I can represent that as a function. And a function like that will look like one of these guys. Okay, so that's just me laying out a lot of the bedrock here. So it isn't just a computer science thing. What we're going to talk about is we're going to be talking about functions. So we're going to imagine you give me one of these complexity functions. I want to determine its asymptotic behavior. That's the goal here. I think we're good to go. So now we're going to talk about and shift gears. We're going to now talk about what big O is. Because now we have everything we're really going to need. going to make sure I check anywhere else, just to make sure nobody else is asking any questions. I think we're good. Okay. Excellent. Okay, so let's talk about big O. So you might ask, what is big O? I mean, I haven't yet defined what big O is. You might be here and saying, Dan, I already know what big O is. Like I said, just lay back, count the number of sheep in the sky, wherever they are. I don't know. The point is that I just want to make sure everybody's got a working definition here so we can actually start doing some examples. Sweet. I like new comments. Awesome. By the way, if you aren't yet subscribed, do subscribe, or also share this with your friends. Like I said, we're gonna have a lot of fun on the channel. We're gonna learn some new stuff. Okay, so what is big O? So I'm gonna formally define big O for you. Now, I might at some point do a proper video talking about the historical origins of big O, but for the purposes of this video, or our stream here that we're doing right now, I want to mention that sometimes this is called Landau symbol. And the appearance of big O notation, at least in its inception, was in the early 1900s. And like I said, it's used very oftentimes to talk about asymptotic behavior. So oftentimes this used to come up in analytical number theory. So oftentimes if I wanted to know about the behavior of, say, a sequence of numbers, say like the sequence of prime numbers, or I want to know if I have some function, I want to know what terms, tendencies might happen for a given number for my function. Remember, think of the machine. If I wanted to determine what's the asymptotic tendencies of a given function, this oftentimes would come up in things like analytical number theory or combinatorics. Yeah, no, that's a good point. That's a very good point. So just keep in mind that this wasn't just created out of like computer science. This is actually something that developed over a period of time. But later on, it's an adoption into the analysis of algorithms type of literature in the, I would say, about the late 60s, 70s especially. Though you probably could find me examples earlier. This was very much prominently discussed by people like Knuth, like Donald Knuth. So if you're looking for kind of like some of the earliest papers really saying like, let's use this type of stuff, you might find some of his papers out there. Some are in the ether of so-called the internet. Surf the web. So let's talk about what big O is. So I already defined what complexity functions are for you. So I got to tell you what I'm going to be using. So I'm going to let f, remember f is going to be a name for a function. I'm going to have f and g. Both of these are going to be complexity functions. So all the statements I'm going to make involve these two functions. So note, they're just names. So I can call these h, I could be calling this k. It's just the name of a function. Just remember, think of it like I had my sticker on my machine where I took an input, I get an output. So I'm going to say f. Now actually I should make a remark before I write this down. Oftentimes you'll find that some people will technically incorrectly write. It's common abuse of notation. They might write f of n. Now remember, you see my picture, I said the output is f of n. But very often you like to have some way of saying what the parameter for your function is. This is a very common mathematical notation, sort of it's a sleight of hand, but it's convenient. So you're oftentimes going to have to forgive me for using it sometimes. I'll say that f, or f of n, but I'll just write f here. F is big O of g. So if somebody writes f of n is big O of g of n, they mean the same thing. Just want to make sure it's clear. F of n is big O of g of n if and only if. If and only if. Now, before we get a little bit further, I want to explain what this phrase means without getting too overly technical with you. So this means that whatever I write on this side is going to be logically equivalent to whatever I write here. So if this is true, whatever I write after this is going to be true. If this is false, whatever's on this side is going to be false, okay? So it's a way I could talk about one side versus the other side. So just keep that in mind if you're not familiar with this phrase. Just think of that. I want to keep things nice and simple. Because very often I find students, like when I've taught this kind of material, sometimes the technical jargon really bogs down the discussion. I really want to just decode that stuff for you. So it's very easy to digest. So f is big O of g if and only if the following. There exists some positive real constant. The fact it's a constant does matter. Constant C and positive integer n0, so that's a subscript, n0, such that, now, the big things I want you to notice here is this term, there exists, it just means you need to find that there is this C and this n0. One's a real constant, so remember, think of real numbers like things like pi, things like that. And the positive integers, these are your 1, 2, 3, 4, 5, your counting numbers. So I want to know that these two constants are going to exist such that the following property is going to be true. Such that for all n greater than or equal to n0, f of n is less than or equal to c times g of n. So what does this mean? It just means that there's going to be some point. Remember, I talked a little bit about this earlier. There's going to be some point. That's what the purpose of this second constant is going to be. There's going to be some point where after that point or on that point, this inequality is going to have to be true. So what do I mean by this? So the way you got to think about it, or at least this is one way to think about it, is I want to find some way or some point where one function is going to so-called dominate the other. So for example, if I have two functions, I'm just plotting out functions here. So this is, say, for example, this is n, and the result outcome here is f of n or g of n. It's the output of the function. And say this one is, say f, and this is g right here. I want to know there's some point n0 where one of these functions is going to start going higher up on my plot than the other one does, and it always will after that point. So n0 could be anything after this dotted or dashed line. Now, intuitively, some students find it a little challenging to figure out why would this other constant be here? Well, it's because I don't really care about a multiplicative value on top of that, because I could stretch this function and it still will just shift where n0 is going to end up going, if assuming it is true. However, to be very clear, I like to usually give the following intuition, is that when we talked about earlier, remember I talked about the steps for which we derived a complexity function, when we talked about an algorithm. So when we talked about the algorithm, we did some sort of analysis. I'm getting so excited here. Let me just stand over here. When we did our analysis, so the idea, we had this step before where we do some analysis on the algorithm. And I told you that there's some model of computation where we count the number of operations that occur given us some situation, like a worst case analysis. So in those situations, you have some number of operations. Now, each one of those operations, like earlier I was talking about baking a cake and having a recipe, you would agree with me that different operations take a certain amount of time. It's a little different, right? Just like on a tangible computer, you would agree with me that maybe like adding two numbers versus performing an assignment of a variable to another one may take a different number of CPU cycles, if we want to get technical. So you would agree with me that the different things we count as primitive or basic operations, say for example for a recipe, whether it be mixing in a bowl, like or whisking in a bowl, or grabbing a spoon out of a drawer, even if we treat them like simple things we do when we bake, or assigning a variable like when we write a computer program, they all actually have usually some number of CPU cycles or some number of operations that actually occur, but we treat them as primitive or simple. So it means that each one of these individual operations actually have some time, like actual time maybe in the physical world, they might actually represent. And I like to think of C kind of like the speed of those operations. Now, it doesn't have to be that. I just find it's very easy to remember it that way. Because when you actually start doing examples with analysis of algorithms, you'll find very much that this C ends up being all of those so-called constants that end up being your CPU cycles. Not always, but very often. So that's at least one idea. Yes, that was an excellent question. So I got a lovely question. It says, but C can have multiple values for which they still satisfy the inequality. Correct. We're going to find some examples where there's only going to be certain values for this C that are going to work, but other ones where like you couldn't use it. But there's so you got to think of this as a pair of constants, C and N0. And sometimes there's a close relationship between C and N0. Where sometimes you could just pick C and then N0 is really easy to find. Other times where if you pick a really small C, N0 becomes very difficult to find. In this series, I'm going to be showing you actually some very, very nice and simple ways to find these two without very much mathematical reasoning, which is really nice. So I'll be giving you kind of a toolbox to tackle some of the more basic types of proofs you might encounter. I plan to do more videos of this nature showing you these things. So we'll be tackling other kinds of functions too, things like logarithmic functions. I'll be talking about logarithms actually towards our final example later on. But let me just reiterate this example one more time. So I'm going to say that f is big O of g if and only if I can find these two constants such that when I have those two constants that I fix them, it must be that after this point, or on this point, n0, when I put in my integer n, it must be that this inequality holds. So just to be clear, remember, the game plan, and I like to think about this like a game plan. Your goal is to find C and N0. That's your plan, but you can't just throw them out in the ether. When you're proving claims like this, you actually have to justify why you picked these two. And how do you do that? You have to justify this part right here, right? That's why it says such that here. So this is what we would call an existential statement on the right side after this if and only if. So your job is to show me that these two constants exist. There might be multiple C's and N0s that work. The point is that your job is just to prove to me that they exist. That's it. You don't have to show me where all of them are. You just have to show me that they exist. That's it. And if you do, then you could say that f is big O of g. Note that you can take this definition and extend it to multiple parameters. So if I have an n and an m and an o or something, some multiple parameters, like multiple inputs, like my machine, where say if I had like 3 inputs instead of just 1, you can also define this thing in terms of that as well. But I'm not going to do that here. Maybe in the future, maybe I'll consider doing something like that for you. Because sometimes that one isn't often as seen often. But this one is very helpful, especially if you're doing analysis of algorithms, because the n is normally going to be the input size or the input length of your problem instance. That's normally what it actually is. So think of it like I feed the input to the machine, n is going to be the length of the input. Or at least it's going to be an appropriate representation of that length. Okay? So that's the definition. Now I want to talk a little bit about how you use this definition. Because there's 2 very common ways we can talk about this definition. You're going to find, hopefully, that they'll have their pros and cons, each one. So I want you, so oftentimes when I teach this thing, in previous courses I used to drill this definition to students' brains. So I recommend getting used to this definition by encountering plenty of examples. Maybe write it down a few times. It really doesn't become very hard to memorize it once you realize that, okay, there's these 2 constants, and that's all I have to do. I have to find these 2 constants. That's the game plan. So as long as you remember the game plan, I find C, I find n0, and I have to just make sure this inequality always holds once I pick these 2. If you remember that, I swear this becomes much easier to remember. You might hear some puppies barking. They're very excited about Big O. So we're going to talk about some common usages of Big O. So I'm going to first show you my favorite because I'm going to be a little biased here. But you're going to find it very intuitive why I would show you this one first. Then I'll show you the other way as well. So because I like to make sure you can see multiple, like 2 different ways you might use this notation. It's very helpful once you see both of them. So these are 2 common usages that so the first one is to, whenever I write the word is, the formal way you can think about is, so when I say f is big O of g, think of it as f is in big O of g. So we would write this like that, where this says is in. So you might be wondering, okay, well then why do you say is? It sounds like it's like means equals or something. You'll see why I mean that later on. But so it's perfectly fine to say when you see f, you see this statement, you could say f is big O of g, or you could say f is in big O of g. Either one is fine. I tend to use this interpretation very often. Now, you might ask what this symbol is. That is some set theory. This is to represent, so you can think of this as a complexity function. It belongs to actually a set, or if you want to get fancy, a class of functions. And these functions are ones related to g. So big O represents a set of complexity functions. So if you want to get very formal and technical here, when you see this big O notation, you should think it's a set. It's not a function, it's not a number, it's actually a set. So you have to be very careful about how you are interpreting things with this big O here, unless you're talking to the appropriate audience, which I'm going to talk about in a moment here. So that being said, now I can show you how you could define big O in terms of a set. So like I said, I'm going to abuse a little notation here. So this is just function. This is G. of n, where g of n is just the name of the function. I'm just specifying the input as n. This is not the output of the function. This is just to make it so I have n to play around with and it's clear to everybody what n is. It's the input for g. So oftentimes when you write sets, use the set builder notation. So I'm going to use curly brackets here, or braces. And I'm going to say that these are functions, f with input n, such that there exists. Now, a mathematically formal way to write there exists is with this backwards e. This means there exists. There exists. So that's just a symbol to represent there exists. There exists c, and c is actually a positive real number, right? So this is the blackboard R representing the set of all reals, but I added a plus here just for my notation, just to say it's a positive real number. So there exists c. Now technically I could put another one of these e's here, but for abbreviation's sake I'm going to just omit it. I'm just going to say there exists c and 0. We established that it's a positive integer. This is a blackboard z. With the plus means it's a positive integer. And then I'm going to say for all. This means for all here. This upside down a means for all. So I'm showing you a little bit of symbolic logic while we're at it, okay? I just want to abbreviate this so you know what these words mean. So there exists for all. So this just means for all n greater or equal to n0. Remember, this is so that I know that no matter what n is, that I could keep pumping in n as long as it's at least n0, that this should be satisfied. Such that, I'm running out of space. Normally you would keep writing it that way. Such that f of n is less than or equal to c times g of n. And that's the end of the definition for my set. So this is actually a set of complexity functions. And notice that this is just the definition of big O right here, right? So there exists c and n0 such that for all of these, this inequality holds. Remember, the inequality is just f of n, so I give you an n. For any one of these n's, it has to satisfy this inequality, where it's f of n is less than or equal to c times g of n. Okay? So one way you can think about it is as a set. Now, you might ask, Dan, why does that matter? Well, very often computer scientists like the idea that you can classify functions into sets or classes. So, for example, you can have, for example, big O of n squared. Big O of n squared. So if you're wondering, n squared is sometimes called a quadratic. So you can have this actually represents all of the functions that satisfy this, but it contains all the quadratic functions that you can think of, but it also contains all the ones that satisfy this relationship. So things that look like, if I were to draw you a picture, so if I gave you a bunch of functions, things like, okay, n squared is obviously, like you'd think that they will probably satisfy this inequality somehow. We haven't done any examples yet, but n squared is going to belong to the set big O of n squared. Other things like n will. Other things like n squared plus n will. The point is that it's a set of functions. So I could start lumping in different running times of algorithms within these sets, then I can compare different running times based on if they belong to a set or if they don't belong to a set. That's where the power of this notation becomes obvious. I'm not going to talk too much about this detail. Actually, I have my series, Advanced Data Structures, on this series. I talk more about that in that series. I'm getting very excited here. So that's one common usage, is that mathematically, big O is a set. This set theoretically means in, or is in, just like C is in the set of all positive real numbers, and so on, and so on, and so on. Correct. Yes. Somebody was asked, lovely question. If f is big O of n, then will it also be big O of n squared, n cubed? Correct. Correct. That's one thing we're going to see in our examples, is that we're going to see that if you have, so if I were to have n squared here, notice n's in here. Notice that other functions may also belong in here as well. For example, the logarithmic function, big O. So if I give you log base 2 of n, that also is in big O of n squared. Why? Because notice that my function, as long as this inequality holds for these two constants that I've picked, we're okay. The way you could think about this is as an asymptotic upper bound. Think upper bound, that it cannot exceed that, given some multiplicative factor to eventually some point. So think about this as an asymptotic as in, remember, think large. There's some point for which it's going to happen. It's an asymptotic upper bound. So that's why you can say, okay, it could be big O of n, it could be big O of n squared, and it could be big O of n cubed, and so on, even if it's n. Hopefully that clarifies that. So it's really, we haven't even drilled into some examples. I'm getting some lovely questions. I'm loving this. These are the kind of things I love hearing. And remember, if ever anything's confusing, you let me know, because I'm here to help. Okay, so this is one common usage. I'm going to show you the other one. So you'll find very often I like to use this notation, but keep in mind it's just the same thing we're talking about. As far as that turtle's still there. So that's the first usage. This is one you're going to run into quite often in practice. And sometimes this is a very useful way of using big O notation. This is why I'm going to show you it. So this is not my preferred way, but you'll find very often it's very handy. Especially if you're dealing with an algorithm that's really complicated and you want some simple way of writing those things down. So one way you could talk about them as sets. So you could talk about one big O being a subset of another big O. Like you could say big O of n is a subset of big O of n squared, or is a subset of big O of n cubed, and so on. You could talk about it like that. But a very common notation as well is this one. And it means the same thing. So be warned. So this means f is big O of g. This is a common convention where this equal sign isn't an equal sign. It means is, not equals. So this is a common convention. And so I'll just write that this is a common convention. You'll find very often that this is used all over the place. So the first one you can think of as like the mathematically rigorous definition of big O, or usage of it. This is the a little bit more lax, but is coherent within the context of its usage. So this isn't an equal sign. The way you want to think about it is if I can take and read the statements from left to right. So you're going to think of this sort of like a one-sided equality. So if I read things from left to right, I can take big O terms, treat them like they're functional terms, and add them and subtract them and other things like that. This is where sometimes it's useful. It's useful in the context of analysis. But I'm going to show you an example of this, and it should become blatantly clear what I mean by this once you see it. So I'm just going to write down that it helps when you want to simplify many terms. So here's an example, and this example will probably make it a little clearer why this is actually kind of handy. So you're going to act like that equal sign is like an algebraic equal sign, but it's not an algebraic equal sign. You're going to see why in a moment. So imagine I gave you f of n, and I told you that f of n is the following. It is 6n cubed plus 20n plus 8. Now, I would like some way of talking about this in terms of big O, but I would like to do that without having to do a whole lot of things. Now, in practice, if you're doing some sort of algorithm analysis, you can imagine f of n being the running time of an algorithm with multiple steps. So say, for example, this is like 3 nested loops. This is a loop, and this is just some set of operations that happen outside the loop. So this is like step 1, this is step 2, and this is step 3 of like 3 major parts of an algorithm. And say you wrote them down like this. Well, what I could do is the following. Watch this. I'm going to take that first term. I'm just going to get rid of the 6. I'm going to drop the 6. Now, you might be familiar with the concept of this kind of rule that you can use where you could drop the constants. So I'm just going to write that as big O of n cubed plus big O of n plus big O of 1. So I'm just going to write down what the term is with respect to n, and I'm just going to ignore any constants. Now, like I said, I haven't done any examples with you yet. I just want to show you this. You can, in fact, check that this will yield, like each one of these individually will belong to each one of these big O terms. So 6n cubed is big O of n cubed, 20n is big O of n, and 8 is big O of 1. So what I've done here is I've obviously abused the big O symbol here, right? Do you see that this is actually, remember, big O is actually, this big O term, this is actually a set. But the way we're using it is trying to represent a whole bunch of different functions. Think of it like a fill in the blanks. So just like if I were to take this and say, okay, each one of these, imagine you could put some other function that looks like 6n cubed in terms of big O. So this could be, for example, 10n cubed or 20n cubed or 10n cubed plus 8. Think of it like a box where you're putting in that term. Now, I haven't talked yet about other asymptotic notations. I'm not going to be doing that in this stream. In a future one, I am, though. So this analogy will not match up perfectly, but it will hopefully help you clarify why exactly this might be helpful. Remember, think of these like different running times of parts of an algorithm. And you could imagine I could put in anything that as long as it's big O of n cubed. But now this is where the neat part comes in. Now, I know something about these functions. Like I said earlier, and in fact it came up in the question, you would agree with me that n is big O of n cubed, right? You probably also guessed that 1 is big O of n cubed. Remember, we're talking about members of a set, but now these are sets, but we're not, remember, these are not legal operations on sets. This is just another way of interpreting the notation. Well, I can take all of these and say, okay, well, which one of these is the most dominant function? At least without the big O's around it. Well, it's the n cubed, right? It's the cubic term. So you see how I could simplify things a little further like this? So now you can say that f is big O of n cubed. But I could do sort of algebra. But you see that this is not nearly as mathematically formal as the first example. But this is very helpful when you're writing things out in terms of analysis. And very often when you want to write down complexity functions, sometimes using this type of shorthand can be very helpful. So you don't have to keep adding in c times something in front of everything. So oftentimes it has its use that way. So the point I'm getting at is that I told you that you could treat it sort of like a one-sided equality, but it's not really an equality, right? As I said earlier, remember, pretending that this is a legal operation on an actual set, imagine I give you this over here. Imagine if I started tweaking around with this side. Would you agree with me that I could just be like, okay, well, now I'm going to modify things on the left-hand side of this equality here? Well, it might not work, because what I'm doing is I'm performing I'm doing one-directional simplifications in this direction. I'm making assumptions based on the fact that it's an asymptotic upper bound, right? So notice that I had this, but I go right here. You'd agree with me that I could pluck out technically a function that looks like that one from here. But this could be, for example, like like this right here, for example, contains the function n cubed, right? Or n cubed plus n squared plus n. You would agree with me that that is not equal to this, right? That's what I mean by it's one-sided. It goes from left to right. So when you're doing this, you'd always write left to right, just like if you're doing some operation on it. Okay? So that's what I wanted to talk about. So just as a remark about this, some people refer to this as an abusive notation, like me. Like some people like me might call it an abusive notation, but it's a very useful abusive notation. So I'm going to say this is handy or useful informally. Now, sometimes people, if they're doing it carefully, they can write this out more analytically. And I'll just say some see it as an abusive notation. That's my neutral way of saying it, abusive notation. So you could use one or the other. Most people in kind of the computer science realm would understand either one of these. So either one of these, some type of, this is one way. You can talk about the is. So you'll very often run in the literature into this representation, but some people still use the set theoretic representation. Okay? So those are two common usages of big O notation. So one way is you interpret it mathematically formally as a set. Another one is that you treat it more like we're talking about the actual functions themselves, and we can perform some simplifications like this. So remember, this means is, not equals. This is not to be confused with actual algebraic statements that involve equal signs. Like I said, I haven't gotten to any proper examples yet, so I just want to show you a few more things, then we're going to do some examples. Okay. So I just want to reiterate some key things for you. Big O acts as an asymptotic upper bound. And I also want to make sure it's clear that you're well aware that there are certain types of functions that people tend to be interested in when they talk about big O notation. So I'll just say be aware of the following. Following well-known classes of functions. So remember, I told you that it's a fancy way of saying what a set is if they're all the same type. It's called a class. Not to be confused with an equivalence class, which is something we could talk about in another video or something. But it's just, these are just a bunch of functions. They're all just of the same kind. Just keep that in mind. Just think of a set. That's it. So I want to make sure you're aware of some of these common ones. So for example, big O of 1. So this will contain functions like any constant function. So for example, if the function just always outputted 8 or 10 or 10,000, they all are in this set. This is called it's sometimes called you just call it big O of 1, or it's just known as constant function. So if somebody tells you that an algorithm has constant running time, that's what they mean. If they write big O of log n, they may specify a base for the logarithm. We'll define what a logarithm is later. So this is often called a logarithmic. So this is often referred to as logarithmic. Like I said, more on this later. Where this is a logarithm. Logarithms normally have a base. But I'm not going to prove it here, but in the future I'm planning to prove for you that, that the base of the logarithm doesn't matter. As long as it's valid. You might know big O of n is linear. You might know n log n. Now, oftentimes people don't give this a name, but a common one I find sometimes in the literature is they call it log linear. As the name suggests, logarithmic linear, log linear. It's not too bad, but usually I just go big O of n log n if somebody's curious about it. Usually people, if you just say randomly log linear, they might be a little, they look at you a little strange. But that is what oftentimes it's called. And we already talked about big O of n squared. That's quadratic. Quadratic. Then if we have big O of n to the c, where c is just some constant that is greater than or equal to 0, we would call that polynomial. We'll talk about polynomials in a bit. So, for example, oftentimes in the algorithms literature, people tend to be very interested in polynomial time running algorithms. So algorithms that run in time that is bounded by any function that belongs to this set. With respect to the input size. But that's, like I said, another discussion. C to the n, where c is just some constant greater than 1, is known as exponential. So these are your functions that are like 2 to the power of n, 3 to the power of n. These are, like if you had an algorithm ran an exponential time like this, depending on the problem you're looking at, you'd probably avoid it if possible. Okay, just 2 more. You might know this one. It's called factorial. So big O of n factorial is known as factorial. So for example, if I give you a bunch of locations you want to visit, and I need to visit all of them, it would be, but like I gave you the most naive approach of doing that. For example, if I just visit them all in any order I would like, technically any valid solution to something like that would be some permutation of all those locations I could visit. And that's roughly something like n factorial. It's not exactly that, but it's pretty darn close. Depending on if you're allowed to go in one direction or the other. Point is that it's based around factorial. Another one is n to the power of n. I don't even have a name for this one. You just stay away from that thing, okay? Unless you know n is some constant, don't do this one if you can. But I warn you that there are things out there in the computational landscape that you can't really escape the running times of things like this. They do exist, but they're things that I'm definitely not going to talk about here or most of my videos. So those are just some common functions I want you to be aware of. If you take an algorithms course, most of these you'll encounter at some point in your studies. Or at least most of these ones on this side and up to about here. Okay, now we can start talking about some examples. I just wanted to get you some setup so we can actually start playing around with this stuff. Now the big purpose of this big O bootcamp is to prove mathematical claims that involve big O. I find very often in my almost decade experience of working with students on this kind of stuff that a lot of students have difficulties proving big O claims. That tends to be a big exercise that a lot of students, especially when they go through, say if they're doing some of their introductory computer science stuff, say in first or second year, usually beginning of second year in their 4-year study, at least that's the case at Canadian universities, they very often will run into exercises where they're asked to prove big O claims. So what I'm going to do here is I'm going to talk about how you could prove some of these claims. I'm going to start giving you a toolbox that you could use. to establish where those two constants are. Remember we talked about C and N0? Your game plan is to prove that those two constants exist. We don't need to show where all of them are, we just need to show that they exist. So your job is just to find them and justify that those are valid selections. But that's one part of it. The other part of it is actually writing it down mathematically in a way that is, one, mathematically correct in its reasoning, but also will convince somebody else that you're correct. And this is going to be the main thing I want to talk about. Like I said, there's a lot of drama building up to this. So let's start off doing some examples here. So the first example we're going to do is I want to try proving the following claim. I want to prove 6n squared is big O of n squared. I want to prove this. Now, if you're familiar with what we talked about earlier, I told you something about that constants in front of functions like this, usually you could drop those. I want to show you an actual example of how and why you could just drop these like this. So this is just a concrete example. You could generalize proofs of this nature as well. So here we go. So I'm going to write out a proof proving this claim. And I'm going to use the definition of big O directly. This is the big part of the exercise. So remember, the game plan is as follows. I'm going to state what the definition of big O is within the context of what I'm trying to prove. Then I'm going to follow from that definition how I'm going to select C or N0, whichever I would prefer doing. And then I'm going to follow from that reasoning to get to the other constant. And hopefully by that process, I'm going to justify the selections of these, and I'm going to write a conclusion. That's at least one standard way of approaching this. Sometimes you might want to simplify the expressions that you write down based on the definition first. You're going to see an example of this probably later. So what's the first thing I usually like to do? I like to say what I'm going to do. So we find constants. Remember, we have to find the two constants. We find constants C. Remember, I told you C is a positive real number. And N0, which remember is a positive integer. Remember the domains of these two numbers. Could you give me N0 as 0? No, because it's a positive integer. The smallest positive integer is 1. So we find these two constants such that, remember all I'm doing is I'm just taking the definition, I'm rephrasing it, such that for all n greater or equal to n0, 6n squared is less than or equal to cn squared. Okay, with this type of problem, I would usually recommend trying to make the thing on this side, right here, look like what's over here as much as you can. So if it's 6n squared, and that's n squared, can I make 6n squared look like something that's c times n squared? Well, I'll give you a tip. Look at this. 6n squared, then it's a cn squared. What should I pick as c? What c would I pick? Think about it. Remember, this is an inequality. So it's okay if they're equal to one another, right? So maybe what I should do is I should pick, so I'm going to say pick, c is equal to 6. Then we need to find what? We need to find n0, right? Find n0 such that for all n greater or equal to n0, 6n squared is less than or equal to 6n squared, right? Well, what do? well, I kind of spell, like, you notice I just spell it out, right? Like, when you read something like this, you want to think about it like somebody doesn't know what's going on in your head. You want to spell out the reasoning, but do it in a concise way. So I pick C, then I say what I'm going to do next. But remember, it's one argument. This is just an argument. So now what am I going to say? Well, look at this. Well, we know 6n squared is equal to 6n squared by identity, right? Like, they're the same thing on both sides. Because you could technically divide both sides by 6n squared. You get 1 is equal to 1, right? Well, now this is how I would phrase this. Well, remember, we need to find that n0 point. That's the goal here, right? Well, for all n greater or equal to 1, both sides of the inequality are equal, right? They're in fact equal. So if they're equal to one another, remember, I need to find that point where they're equal or it exceeds it, right? But in our case, the C I picked, they're just going to line up perfectly at all times, which that's okay. So I'm going to choose n0 is equal to 1. And we're done. Now I need to put this all together, right? I need to gift wrap the proof, right? Therefore, by choosing such constants, by the definition of big O, I'm just going to abbreviate definition with def of big O, the definition of big O, 6n squared is big O of n squared. And we're done. Note that this box here is just me indicating the end of the proof. So this looks a little wordy at first. You maybe you feel like you maybe can somehow make this a little shorter. You can. But I like to show all my reasoning like this. So I say what I'm going to do. I tell you what I'm going to select. Remember, because this is an existential statement, I just need to show they exist. If I pick C, my goal is then to justify if I pick an appropriate n0, the inequality is always going to hold. That's the whole trick I'm using here. So notice I never justify picking this C. I don't do something to spill it out. This is where the intuition of my proof comes from. So that's the whole trick. Now, the whole strategy I used here intuitively was to make whatever's here look like what's over there. So that's the strategy I used here first, right? So really, it's nice and easy. So that's our first example. So the first strategy that I like to give is try to make what is on the left side of the is look like whatever's in the big O. That's the first thing I usually recommend. I think we lost the turtle. The turtle's gone now. At some point, the turtle ditched us. Whoops. Okay. So that's one example. Let's do another example. Let's see if we can use that same idea again. So here's a second example. What we're going to do is we're going to prove that n squared plus 12n is in, or is, big O of n squared. Now you might ask, Dan, why are you picking n squared, not n? Well, remember, I'm pretty sure that it won't work if this is n here. I'm not in this stream going to show you how you prove that it doesn't work. That'll be something I'll do in the future. But I want to just show you here that we're going to try using the same idea again. But we're going to extend this a little further. And by doing this, I'm going to show you actually a more general strategy that actually comes out of the idea that I showed you in our previous example. So I want to make whatever's here look kind of like that. So I have something that's n squared plus 12 times n. I want to do something with c to make it so that this thing looks a lot like that. And if I am able to bound the inequality correctly, we're done. So let's write out a proof. So remember the game plan. We want to find c and n0. Our job is the inequality comes from the selections of c and n0. That's the part where we actually have to justify our constants that we select. So here's our proof. We need to find constants c, which is a positive real constant, right? And n0, which is a positive integer, such that, gotta make sure I put my comma in, need a comma, such that for all n greater or equal to n0, what do we want to do? We want to say that n squared plus 12n is less than or equal to c times n squared. Now this looks a little different than our previous example. Why? Because there's two terms here. What I would like to do is I would like to take this n squared and try to make it look kind of like this, but make it so it's bigger than what's on the left-hand side of the inequality for an appropriate value for n or greater. Does anybody see any idea like the one I used last time? Well, I have n squared, and I have 12 n's here. Maybe if I make 12 n squared terms here, maybe I can create something that looks like that. So I'm going to pick c is equal to 13. You're going to see why 13 works really nicely here. Pick c is equal to 13. Now this is the major observation I'm going to have in my proof. Notice that for all n greater or equal to 1, we have the following chain of inequalities. Now, chaining of inequalities looks a little daunting at first, but don't worry, it's not actually that complicated. I'm going to show you what kind of reasoning I'm using with a demonstration shortly. So I'm giving you my backup here. So this is an observation I'm making in my proof. This observation is what gets us to the conclusion. Notice that for all n greater or equal to 1, n squared plus 12n is going to be less than or equal to n squared plus 12n squared, which is of course equal to 13n squared. Now, I haven't yet justified why this is true, right? You have to make sure when you write something down like this, you need to justify it at some point. Now, this part is obvious. I say the domain, I'm saying that this statement is true, and I'm going to give you my reason why now. As n squared is less than or equal to n squared for all n greater or equal to 1, and 12n is less than or equal to 12n squared for all n greater or equal to 1. Now, if you take a look at these two simpler expressions, what I do is I'm going to add them together. I'm going to add these two inequalities, the terms on both of the sides, to each contributed side, and that's actually how I get this statement, this chain of inequalities here. How do I know that this statement is true? Well, if you divide both sides, because remember, I'm assuming that n is positive, right? So if I divide both sides of this by n squared, I end up with 1 is less or equal to 1, which has to be true for all n that are greater or equal to 1. Then, notice that I have 12n is less or equal to 12n squared. Notice that if I divide both sides by 12n, I end up with n is greater or equal to 1, right? So that's how you could justify these if you want to break it down in the further steps. Now, I want to show you exactly why this all works the way it does. So I want to show you where this comes from. So I find this is easier to explain using actual things. Okay, now imagine I was trying to show you that two statements of quantities were equal to one another. Now I have two buckets here, and I have some objects. They're all the same size, they're the same objects. So just imagine these as quantities. You'd agree with me that if I put one of these bottles into one of the bins, and I put one of these into the other bins, you'd agree with me they have equal quantities, right? They have equal quantities. You'd also agree with me that if I added in another pill bottle, or bottle, whatever this is, into another one in each one, you'd agree with that the quantities are still equal, right? If I took and totaled these up, right? So each one has 2 in it. Just like if I had added another one into each one of these again. Okay, you'd agree with me that that makes sense, right? It's coherent. It's sound. I'm going to use the exact same type of reasoning. So it's a similar setup to what I'm doing here. So I have, these are my two buckets. I have, this is my left, this is this bucket, this is that bucket. Now, if I know that they're equal terms, it's no different than like if I stick one of these each in each bucket. But if I know that one other bucket, say if one side of this inequality actually contributes more, then we know that that side is at least the amount on the left-hand side of the inequality. So for example, if I have 1 here and 2 here, you'd agree with me that the ones in this bucket are at least, is going to be no more than what's in here, right? So in fact, if I switch these two around, it's kind of like if I had these two inequalities here. So all I'm doing is I'm adding up the two sides of the inequalities together to get two kind of super inequalities. So I'm just summing over two inequalities, this one and that one. So I'm just taking n squared, and then I'm adding 12n and 12n squared. 12n on this side, 12n squared. So I'm just summing over the inequalities, because I know that this is less than or equal to that. In fact, they're equal. It's no different than me putting these in here. However, the second one over here, it's very possible that the right-hand side of that inequality is going to be larger. It's no different than if I took 2 of these pill bottles and I put in one in here. So it's really just the same idea being applied. Does everybody see that? So it's actually not that complicated. I find, so just remember, the reason why this works is I'm summing over inequalities. So I've taken each bit in piece comparatively. So I have the n squareds, and I have the 12n and 12n squared. I sum each one of these inequalities together. I sum over these two, and that's how I conclude and get this statement. So all I'm doing is I'm just taking quantities of equal or greater amounts, and I'm dumping the one into a larger bin than the other one. It's really just that simple. So if you understand this reasoning here, we can generalize this further, right? I'm going to show you how you can generalize this even further with a more complicated example. But I just want you to observe that I'm using this kind of bucketed inequality approach. It's not the technical name for it, but I like to think of it like I have this term and I compare it against that term, and I have this term and I compare it against that term. If I add this to that, I add both inequalities together, their respective left and the right sides. I end up with this chain of reasoning. the 13n squared, this is c right here, right? What's n0 then? What's n0? n0 is 1, right? I just told you it. It's right here. Notice that for n greater or equal to 1. Choose n0 is equal to 1. I'm just going to switch markers here. Therefore, by the definition of big O, n squared plus 12n is big O of n squared. And we're done. So the core of this argument, notice I didn't do any crazy analytics with you or anything like that. All I did was I compared terms, then I added up the terms. Because you'll notice that I have this. I know this is going to be less or equal to that. And I have this. I know I demonstrated that's less or equal to this. I broke it down into simpler pieces, then I just added them all together. Easy peasy stuff, right? Notice that I didn't need to do any root solving or anything like that. I didn't make any assumptions about the functions increasing or anything like that. Those are some assumptions you can make to do some other techniques like root solving, which is another technique that some people like to use when they're proving claims like this. Okay. So let's do another example. I'm hoping that you're starting to see a pattern, but this will hopefully help pin it down. Let's do another example. So hopefully this will hammer the idea in. I'm going to do something a little bit more complicated. So we're going to prove that 4n to the power of 4 plus 3n cubed, or to the power of 3, plus 2n squared plus n is in big O of n to the power of 4. So remember, I want to make what's here, I want to kind of make it look like something like this. And then what I want to do is I want to chain together inequalities and then add over those inequalities. Because once I have that, like my buckets, I get the chain of reasoning I want for a desired n. And you'll see quite quickly how n0 pops out of this reasoning. And I want you to also notice that when I break them down into those atomic pieces of inequalities before I add them all together, each one of those is very easy for you if you need to further demonstrate that each one is true. The point is that you're summing over the inequalities to derive the overall inequality. Okay, what do we normally do? We state what we're going to prove, right? We need to find a positive real constant, constant c, and positive integer constant, constant n0, such that for all n greater or equal to n0, 4n to the 4 plus 3n cubed plus 2n squared plus n is less than or equal to c times n to the power of 4. Does anybody have any ideas of what I should pick for C? Does anybody see it? What should C be? Well, last time, did you see how I got C? I looked at the coefficients of the polynomial that I was looking at. That time I had a quadratic with some linear term there. So maybe I should look at this and maybe I might have a general pattern I can use. And that might give us a rule that we would like to have. So let's see here. I want you to think about this. Do you see it? Well, I'll give out some reasoning here, and this shall hopefully help spill out what C should be. I'm going to pick C is equal to 10. Then we need to find n0 such that for all n greater or equal to n0, 4n to the 4, 4n to the power of 4, plus 3n to the power of 3, plus 2n squared plus n is less than or equal to 10 to the power of 4. Well, 10 times 10 to the power of 4. Well, here you're going to see quite quickly. I'm going to use the same strategy. Well, observe that. So this, like I said, you'll notice that a lot of these arguments I use rely on an observation. They rely on an observation. So what I'm going to do is I'm going to try to turn this right-hand side into something that looks like the thing on the left-hand side, but with different powers. And if the powers are more dominant than the ones for each individual term on the left-hand side, we're done. Then I can find n0 pretty quickly. Well, observe that. Actually, I'll try writing it here. Let's see how small I can write this. Observe that 4n to the 4 plus 3n cubed plus 2n squared plus n is less than or equal to what? I'm going to rewrite that in terms of different terms that are powers of 4. 4n to the 4 plus 3n to the 4 plus 2n to the power of 4 plus n to the 4, which this is equal to 10 times n to the power of 4. Do you see where C came from now? All I've done is I've distributed 10n to the power of 4. I split it apart into these 4 different terms. Then what I'm going to do is I'm going to compare each one of these against each one on the left-hand side of the inequality. So now here's the part where I justify it. So I'm saying observe that this is true for all n greater or equal to 1 as, I'm sort of going all the way over here. Hopefully I didn't attack the microphone there. As, now here's the reasoning, 4n to the power of 4 is less than or equal to 4n to the power of 4 for all n greater or equal to 1. 3n cubed is less than or equal to 3n to the power of 4 for all n greater or equal to 1. Do you see how this one's true? You just divide by 3n cubed, right? Then you get n is greater or equal to 1. And then we have 2n squared is less than or equal to 2n to the power of 4 for all n greater or equal to 1. And that n is less than or equal to n to the power of 4 for all n greater or equal to 1. So I'm just using the same trick. Remember, it's nothing too crazy. I'm just trying to make what's on the left-hand side of the inequality look like something I could put on the right-hand side. That's how I pick C. I find picking C makes things much easier when you're dealing with things like polynomials. So now this is my justification. What's n0? I'm just going to choose n0 is equal to 1, right? You'll see that if you pick C appropriately a lot of the time, you might get n0 being 1. That is not always true for general functions, but you'll find that I'm going to give you a recipe that you could use for any polynomial of a form like this. So, like I said, this is all just a big set of tools I'm giving you that you could tackle any polynomial. So, here we go. Therefore, by the definition of big O, now let me write all that out. 4n to the power 4 plus 3n cubed plus 2n squared plus n is in big O of n to the power 4. And we're done. Notice, remember, same structure. You'll notice I'm just doing more complicated examples now, but they're all based on the same idea. I try to make something look the same on the opposing side. Whatever's in that big O, I want to make that look like what's over there. And I may have given you a recipe to do that quite quickly. So I say what I'm going to do. I pick C or N0. I don't have to pick C first. You can pick N0. I just find C is much easier to work with than N0 if you know what you're looking for. That's the intuition. Because not every mathematical proof just kind of spells itself out when you see it. Oftentimes, sometimes computer scientists, mathematicians, they could sit there for months trying to prove a claim. These guys, they're nice and cute. But they aren't obvious the first time you look at them, and that's cool. That's perfectly fine. When you first learn something, don't expect yourself to feel like you've already mastered it. It takes time to learn things like this. So hopefully you'll see that we're starting to build actually a tool that we could use to prove any one of these claims. And now I'm going to give you the tool. Okay. We're going to talk about polynomials. Remember earlier I talked about what a polynomial looks like, the form of a polynomial. But let me define what the ones that we usually are interested in look like. Polynomials we are interested in usually have the following form. So they have the form, I'm just going to call it P of n. P of n, where it's going to have coefficients. The coefficient is just the term that sits in front of the term that's a power of n. So I have my base here is n to the k. So it's a sub 0 times n to the k, a1 times n to the k minus 1, plus a sub 2 times n to the k minus 2, so on until a sub k to the minus 1 times n to the power of 1 plus a sub k times n to the power of 0. Now it's worth noting that it's n to the power of 0, that's just 1 here. So you'll end up with just a sub k times 1, or just a sub k. This can be rewritten in terms of summation, a summation like this. I've just given you a finite series. That's the fancy name for I add a bunch of terms together. Each one of these has a special name called a coefficient. This is the term that is relative to n. So these are fixed. K is also fixed. That means that they don't change, but they could be any fixed one. So you could put them down, but they aren't just arbitrary here, okay? They aren't variable within. So this summation just simply means what I've written here. This is just an index that allows me to go from 0 up to k, and I just add up each term as you appear it, as you substitute in I. I haven't told you what the coefficients domains are, where coefficients a sub 0, a sub 1, and so on, all the way up to a sub k. Now, I'm going to assume them to be non-negative. That means that they're 0 or they're positive. That's very much what you run into when you're adding up parts of a running time of an algorithm. But it's worth noting that the technique I'm going to show you can easily generalize to where these are just arbitrary real numbers. So you don't have to have it where it's only positive or 0. It could also be negative. It just takes a small little tweak in my proof that I'm going to show you. So it's just a small little tweak. So now, believe it or not, this whole trick I've been showing you where I try to make something look like the opposing side that is in the big O notation, it actually can be viewed in a very, it's actually just a strategy that looks like this. I like to think about it like this. I want to think about it like a light switch. So imagine I have a bunch of light switches. I'm going to have 5 light switches. Please don't mind my drawing. I'm kind of doing this quickly. There's a better one in the notes, by the way. The notes are available on Patreon or Subscribestar. So, let's see. I have all these, but I'm missing the switches, right? I need switches. So let me put some switches on all these. So here's switch. I'm going to assume that up means it's on and down means off. Now what each one of these is going to represent is a part of a polynomial. So whether I include it as a part of the polynomial or I don't. So here's a sub 0 times n to the power 4, a sub 1 times n cubed, a sub 2 times n squared, a sub 3 times n to the power 1, and I have a sub 4 right here. Now remember, that's n to the power 0, so it's just... So this is an example of a polynomial. Now, I want to think about the example I just gave you before. Do you remember the coefficients of that polynomial? It had 4, 3, 2, 1, and I believe, I think it was just 0, right? Let's see. So I have plus 4, plus 3, plus 2, plus 1, and plus 0. So what did the polynomial look like before? What did it look like? What did it look like? Did it have a constant term? No, it just had, it was something to the power 4, something to the power 3, something to the power 2, then something to the power 1. Nothing for when it was 0, right? Like n to the power of 0. So what I'm going to do is I want to imagine these as a bunch of light switches. And if that's a part of the polynomial, I turn on the switch. So if I were to plug in my a sub 0 as 4, a sub 1 as 3, a sub 2 as 2, a sub 3 as 1, and a sub 4 as 0, you would agree with me that if I toggle these switches correctly in the right combination, it'll look like my example from before. What did we know? We know that if I included all the terms except for the final one. The final one did not have a constant term except for 0, right? So I just got to make sure that light is off. So all of these have lights on. And you might ask, how do I select C? I add up all of the numbers that are on the light bulbs for lights that are on. So remember, I picked 10. It's because in my polynomial, all of the terms that appear in the polynomial, they'll all have a causative coefficient. And the whole strategy was I was trying to make all the terms on the left-hand side be ones that are less than or equal to a term on the right-hand side. What do? I use a more dominant term, like a power that's greater than its own power, with a coefficient that matches it. So all I do when I select C, and this is what I did for every single one of the examples, I just didn't tell you until towards the end, is I've added up all of the coefficients. That's all I did. So if a term appears in your polynomial, you'll have a coefficient. Just add up all the coefficients of the polynomial, pick that as C. And you'll see that that strategy we've been using this entire time will work. It will always work for a polynomial that looks like this. And it can be easily modified to make it work for any polynomial. So let me show you. So I like to think about it as light switches, where if that term is in the polynomial, you turn the light switch on. If that term isn't in the polynomial, I turn it off. So for example, if there's no n squared in the polynomial, I turn the light switch off. I don't add it, even though it technically would have a coefficient of 0. So all I do is I just add the coefficients. And that's the strategy. You could use this strategy dealing with almost any polynomial you're going to run into. As I'm going to show you, it always works. So now I'm going to prove that to you. So just keep in mind P of n, or P, that's going to be what we're going to prove our claim about. So here's the claim. So here's a theorem. So theorem is just a fancy statement that is a mathematically true statement that has been proven to be correct. So given constant k greater or equal to 0 and coefficients as before, so that was just on the board before I got rid of it, I'm claiming that P of n is big O of n. Running out of space here. This is why I like having both boards. P of n is big O of n to the power of k. So you get any polynomial. So you have a polynomial, you can say it's big O of a polynomial. But the polynomial is going to end up being basically the dominant term of the polynomial. But I'm going to give you a proof now. And this proof is very simple, surprisingly. It's going to use the exact same strategy I just showed you before. And that's really it. It's going to use the same idea, this bucketing strategy I showed you in a previous example. So remember, like I said before, So remember, as I said before, the whole idea is that if I know two terms are equal to one another, think of them like the sides of the inequality as quantities in total that I add together. If they're two equal quantities, the two sides will remain equal. However, if one side has more, then we say that this is going to be bigger, at least, than what's here. So we're going to use that idea, the same idea I used before. So here's the proof. Remember, we just say what we normally do. We just want to use the definition of big O. We find constants. C, which is a positive real constant. And N0, which is a positive integer, such that for all n greater or equal to n0, I claim that if we can find the c in n0, that we can show that p of n is less than or equal to c times n to the k for some constant k. So I'm going to use the strategy I laid out before with the light bulbs. I'm going to pick c is equal to a sub 0 plus a sub 1 plus da 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 all the way up to a sub k. So this is, so you would read this as a sub 0, a sub 1 to a sub k. So you just add up all these terms, which this, by the way, is just a summation of all my a terms, all my coefficients. A from I is a 0 up to k. Little cramp there. So I'm going to pick this as my constant. Remember, it's just a constant. All these coefficients are fixed, so I can pick that as the constant. Now I'm going to use the exact same thing I used before, but it's going to look very general. So if this looks a little daunting, go back to one of my previous examples and try this with some smaller polynomials. Then observe that for all n greater or equal to 1, P of n is going to be equal to following. Remember, we wrote down that as a summation, we wrote down that a polynomial is just the sum from 0, I is equal to 0 to k of a sub I times n to the power of k minus I. This is going to look eerily similar to you because this is just my bucketing approach, just the buckets. Just don't overcomplicate it. It's just buckets. All I'm going to do now is I'm going to just ignore this minus I part. I is equal to 0 to k of a sub I times n to the power of k. Now you might ask, where the heck did this come from? We use this actually. And the one thing I love about mathematical proofs is they inform you of things that you would otherwise not observe unless you've seen the general pattern. So you notice that this is actually just, like, remember all those chains of inequalities I showed you before? It's really this. Do you see that? So notice that before we had it where we were comparing like n squared against n cubed or n versus n to the power of 4. Well, those are your n cubes and n squareds and n's. These are your n to the power of 4s from our previous example. Which this is actually equal to the sum of all of those ai terms from I is equal to 0 to k. Now, you'd agree with me that every one of these terms here is really just a sub I times n to the power k, but notice that n and k aren't dependent on I, right? So really this is no different than if I summed up all of these a sub I terms. I add those all together, then I multiply by n to the power k, right? It's no different than if I added up a bunch of multiples of 3 then as opposed to multiplying it by 3. It just It's just another way of viewing the same thing. Or at least that's the same general gist. So I'm just going to factor out of this summation n to the power k because it doesn't depend on I. Remember, k is just some constant, so it's just n, but n isn't dependent on the summation at all. It's no different than if I was multiplying out some constant if I fix n. Remember, n is variable with the polynomial. Now, as with before, I have to still justify the statement to you, right? Now, let me give you the most general form of all those inequalities I wrote. You know how the last example I gave you this really... It was a lot of inequalities where I was saying as n is greater or equal to... Like, for all n is greater or equal to 1. I could do the same thing here. But I recommend that you look at this carefully. As a sub I times n to the power of k minus I is less than or equal to a sub I times n to the power of k, which is equivalent to me writing, this is if and only if. Remember I said before, this is just going to be a logically equivalent statement to this inequality. Is if and only if 1 is less than or equal to n to the power of I, for all 0 is less than or equal to I is less than or equal to k, and n is greater or equal to 1. Now you might ask, Dan, that looks a little daunting. All it is remember, this is, if you actually tried expanding out our examples, it would actually just be this. Remember where I told you just divide by both sides? We've been doing that every single time where I told you, well, yeah, it's not hard to argue that. It's just this. So what should n0 be? What's n0? It's just 1, right? So choose n0 is equal to 1, right? Therefore, by selecting such constants c and n0, by the definition of big O, P is in big O of n to the power of k. That's a left parenthesis. The microwave sort of melted my parenthesis. And that's the end of the proof. Do you see how what we've been doing with all these examples is actually all just a special case of this argument? If you don't see it, just take your time. Just try writing out with this, let's say, for example, k is equal to 2 or k is equal to 1. And try to make the examples I showed you before, just plug in the coefficients for the polynomial as I wrote it. And you'd get this. Now, I'll give you a little bit of an interesting insight. I told you that it's very simple to modify this so that it works for any polynomial of the form I gave you, where the coefficients are positive, negative, or 0. Believe it or not, it's really not that hard at all. I'll give you a tip, and I'll let you think about it. Try taking the absolute value of all the coefficients, and then see if you can use the same chained argument like this, the same set of inequalities like this. See if that still works. I'll let you think about that. So remember, the absolute value will then take away the sign of the coefficient, instead it just makes it positive. I'll let you think about that. But that's a general recipe you can use to tackle any polynomial. So just add the coefficients of the polynomial as they appear in it. So I recommend when you're using this, just simply write out the polynomial. If there's any terms omitted, just write down 0 times that power. And you can see right away what coefficients you should add. Or if you just are familiar enough with this, just add the coefficients as you see them. Okay? It's really just a lovely power that you can use for this. And just think of a light switch. Is that cool? Okay. So, okay. We're reaching actually almost to the end of this session, believe it or not. Okay. Okay, here we go. Believe it or not, we're actually approaching the end of the session. We're actually, well, at least this session. Believe it or not, we're actually doing the last example of this bunch. And this one's going to be a little tougher, so I'm going to get rid of the hat. That means it's serious business. So we're going to do ourselves one last example before we wrap things up. So here's the example. Now, before we get to the example, I have to give you some terminology. We're going to talk a little bit about logarithms. Talk a little bit about logarithms. So I'm going to assume that you're given some variable x, which is going to be some positive real number, and a valid b. I'll just assume it's bigger than 1, but as long as it's not equal to 1, you're generally okay. But I'm not going to worry too much about that. I'm just going to assume that b is greater than 1. It's not a big issue for us, at least here. We might need to be more particular if we were talking about the logarithms in a different context. I want to ask you a question. What power y is so that if I give you b to the power of y is equal to x. So I give you x, and I know b. What's y so that b to the power y is equal to x? Now, if we look at this a little bit differently, imagine if I give you b and y, you'd agree with me that this is just computing the exponent, and I get a result x. I'm asking you an inverted question, the inverse. I give you b, I give you x, I want to know what y is. So what was the exponent you raised it to so I got x? So let's think about that. Let's consider powers of 2. So for example, I'm going to write down some powers of 2 for you. So I write down 1, 2, 4, 8, 16. So this would be what? This is 2 to the power of 0, right? That's 2 to the power of 0. No, it's 2 to the power of 1. I'm getting ahead of myself, literally. See, there's 2 to the power of 0. There's 2 to the power of 1. Got 2 squared. 2 cubed. 2 to the power of 4. And so on, right? So if I give you 2 to the power of n, this is no different than me writing 2 to the power of n, right? Just the same thing. And I ask you, what was the exponent I raised? So if I gave you this number, what was the exponent I raised 2 to get that number? Right? That sounds weird at first. So if I give you 1 and I give you 2 and I ask, if I give you 2 and I raise it to something, what's the something that gets me? Same idea here. So this is what y is. So if we're considering powers of 2, that's going to be example or relative to, I believe my example, I think that's actually quite relevant. So what is the exponent here? It's 0. Because if I go 2 to the power 0, I get 1. If I go 2 to the power 1, I get 2. I go 2, 3, 4, and n. So, do you notice that if I ask what the exponent is, it's just y. But what is that? So a function that describes y is called a logarithm. I was about to say is a called. I'm not Mario today. It's called a logarithm. Like I said, we're at the beginning of this thing. It's called a logarithm. So all you really need to think about is think the following. This is at least one way I remember it. It's the inverse of exponentiation. So I raise something to an exponent, I get a result. The inverse of that is I get a result and I know what I had as the base. I want to know what I raised, what was the exponent that got me that result. Exponential. I was getting ahead of myself. Exponentiation. Please don't mind my spelling today. It's a little strange today. I think that's fine. Okay. So instead of wanting x, I want what y is, right? So I'm going to give you some examples. So example, we write this as log with a base. B is the base. So B is the base. And then this is x. It's not an example, it's a definition of a logarithm. So we write log base b of x is equal to y. So for valid bases and valid x, there's y. So we'll call this log base b of x, and that's what a logarithm is. I have more details in the notes. So I want to do some quick examples just to illustrate the notation I've written here. So for example, log base 2 of 8. Well, look at our picture. Look at what we plotted out here. Okay. So I want to know what was the exponent I raised 2 to get 3, right? This is y. How about log base 2 of 2 cubed? 2 cubed is just 8, right? So it's also 3. How about log base 2 of 1? Log base 2 of 1. It's just 0, right? Because to get 1, you have to raise the power. Right? The exponent has to be 0, right? It's worth noting that there are a lot of properties that logarithms actually have. For example, I can take the exponent of the base. So if this is the power, if this is expressed as a power, I can drop the power out in front of the logarithm and multiply it. I can't recall if we're going to need that in our proof, but it's an interesting fact. There's a lot of properties that logarithms have. I recommend you check it out. I may do a video on it in the future, or it might exist by the time you watch this. So now that brings me to talking about what I want to do next. Like I said, this is some fun business next. We're going to write some fancy stuff out. Okay. I'm going to define another concept called a harmonic number. Now these numbers pop up sometimes they have a very strange fact that they pop up in strange applications. I'm not going to talk too much about what harmonic numbers are used for, but I want to bring up the harmonic number because the harmonic series sometimes pops up in various applications. And I'm not going to talk about those applications here. I just want to define what it is because it's a nice fact to know on the side sometimes. So given some integer n greater or equal to 1, I'll give you some positive integer. The nth harmonic number which I'm going to call h of n, I'm going to express as a function, is equal to the sum of our so-called finite harmonic series. It's going to be the sum from I is equal to 1 to n of 1 over I, which if you write this out, it'll be 1 plus 1 half plus 1 third, 1 quarter, all the way up to 1 over n. As a remark, sometimes people write the nth harmonic number as h with a subscript n. But for simplicity, I'm just going to write explicitly as a function. So this is what a harmonic number is. One thing I want you to know about that's interesting about the harmonic, this finite harmonic series, or the nth harmonic number, is actually it has a logarithmic relationship. So what we're going to do, so this is the final thing we're going to do, at least here. So the next example, what we're going to do is we're going to prove that the nth harmonic number is big O of log base 2 of n. So this is what we're going to prove. This is going to be the last thing we're going to do. A little bit of a more interesting example, because this one doesn't, it will not fit into the trick we used. I like to challenge you on some things sometimes. So I'm going to do the same thing we've done every single time. I give you what we're going to do, then I'm going to do some observing, and that observing will allow me to continue the argument to its conclusion. So I'm just going to have an argument that's going to lay this whole thing out. But you're going to see I'm going to have a little bit more setup here. There's going to be a bit more setup. So we need to find C. Remember, these are constants. We need to find C and n0. N0 is a positive integer, remember. So that for all n greater or equal to n0, we want to prove that h of n is less than or equal to c times log base 2 of n. Now, I'm going to require doing a little bit of an interesting setup here. I'm going to create another thing that I want to compare h of n with. And I'm going to do this because sometimes n could actually not be a power of 2. This makes things a little bit more complicated for the analysis, but we're not going to talk too much about some notions such as smoothness, which would allow us to make assumptions like that. Here at least, I might talk about that in the future. But here I'm going to bring up some setup here that allows me to just assume any n. Because when you assume n is a power of 2, this proof actually goes a lot faster. So before we do this, let n be rounded up to the next power of 2. Power of 2 call it m. So it's going to be m, and it's going to be equal to 2 to the power of the ceiling of log base 2 of n. Now, you're wondering what the ceiling is? So if I write down the ceiling of x, this just means x rounded up. So for example, if I give you 2.3 with the ceiling on it, I want 3. I'm just going to keep it simple here. So for example, if the number that ends up being, like say for example, I give you 8, we know that 2 to the power of log base 2 of 8 is actually equal to 8. That's because logarithms are, like I said, inverse to exponentiation. So if I take the exponent, the inverse operation, that is taking a logarithm. So if I take 2 to the power of a logarithm, and this is base 2, if in fact this ends up being something that is in fact a power 2, what should I get back? So if this is 2, so like say for example this was 8, like n is equal to 8. We know log base 2 of 8 is equal to 3, right? Well, 2 to the power of 3, 3 rounded up to 3, right? Because 3 is an integer, right? So that's just 8, right? So this is just, so m is just going to represent the next rounded up power of 2 of n. So it might be n. So m might be equal to n, but it might be bigger than n. So I want you to note, note that n is less than or equal to m. That fact is going to be important for us later. Then I'm going to define k. So this is going to be another thing I want to work with. I'm going to say k is going to be equal to the ceiling of log base 2 of n. So remember, the ceiling will just round up the result of whatever's inside those ceiling brackets. So the reason why I want this is so that I have something to easily represent the log base 2 of n, so I don't have to write it every single time. I can just write k instead. And I can write things like this. Now, I'm running out of space, so I'm going to erase the definition of a harmonic number so I can get some more space. Because this is going to be where most of the meat potatoes will going to happen. So, and now this is just going to go up here. And I can rewrite this now as the following. I can write the nth harmonic number as chained together with an inequality that looks like this. Well, what's the definition of the nth harmonic number? It's just 1 over I, where I is equal to 1 to n. Now, you'd agree with me, because n is less than or equal to m, that if I sum up to m instead of n, that this inequality should hold. Because we know n is less than or equal to m from the way we've defined m. Remember, it's the next highest up power of 2 from n. It might be equal, it might not be. But what is that? Now, since I have something that looks like a power of 2, it makes it easier for me to work with this. What is this? This is 1 plus 1/2 plus 1/3 plus 1/4 plus all the way up to 2 to the power of k. And this thing that I've just written here, this is h of 2 to the power of k. And if you're remembering, you'll notice that this is just simply me rewriting some of the things I have over here, right? Because what's k? K is this, right? So this is just me making it a little easier for myself to write it down. You can write the whole thing out if you'd like. The point is now I have a relationship between the nth harmonic number and another version of the nth of the 2 to the power of kth, or h of m, right? It's h of m that will allow me to get ahead of myself here. So now what I'm going to do is the following very, very fascinating trick. Now this is the heart of this proof, so I'm going to be I'll be very careful here. So I'm going to erase the rest I have down here. I have to be very careful. Then we can formulate a second series. Second series as follows. Okay. So what I'm going to do, I'm going to write down my original series on the left-hand side. And then what I'm going to do is I'm going to formulate another series on the right-hand side. Now you can write out mathematically as a summation the right-hand side. I'm not going to do that here because it just doesn't add anything to the discussion. But if you really want to pin down and write it out, it's probably out there. You probably could find it. So you'd agree with me that our harmonic series might look something like this. Now, I should stress that we're interested really in something that looks like this, right? Because remember, this bounds from above this. So if I can say something about this finite sum, then I'm done, right? I have something that relates h of n to whatever the second series is going to be. So the first term in this finite sum is 1, right? So I'm going to just write 1 on the right-hand side. I'm going to pair terms by a given number of terms that are based on the power for which they represent. So that sounds like a lot, so just please bear with me. I'll be patient. So the next two terms in the series here are 1/2 and 1/3 here. You'd agree with me that if I replace that 1/3 with 1/2, that this should be at least that, right? So I'm going to replace those two terms with 1/2 each. Then I'm going to take the next 4 terms. So notice I have 1 term, then 2 terms, then I'm going to have 4 terms. So I'm just going to write out those terms based on the power that's related to. So here's the next one I want. So I'm going to have the next 4 terms. 1/4, 1/5, 1/6, plus 1/7, right? Now you'll notice that the way you can tell really quickly how many terms I'm using is you'll notice that the denominator will represent the powers of 2. That's going to be an important detail when we're drawing this out. So we have 1/1, which is 2 to the power of 0, 2 to the power of 1, 2 squared, well, 2 cubed, and so on. So all I'm doing is just I'm writing out, I'm grouping terms based on the number of terms given that power. So here I write out twice because so I write it out twice because it's 2 here. I write out 4 times because it's 4. You would write out 8 times because it's 8 in the denominator, and so on. You'd agree with me that the first term is less than or equal to 1/4. The second term is less than or equal to 1/4. The third term is less than or equal to 1/4, and the fourth term is less than or equal to 1/4. Then what do? We just keep doing this. Now, what I would like to do is there's something that isn't quite right with this series. I have to be careful. but I'm going to show you at the end. Do you agree with me that there's still a term that I might have to account for? It's this one over here. I don't want to spoil it yet. So if I keep writing this out, the general pattern I'll get, it looks like 2 to the power of k minus 1 plus 2 to the power of k minus 1 plus 1 plus 1 over 2 to the power of k minus 1 plus 2 plus 1 over 2 to the power of k minus 1. Notice that the term on the right side of all these sums are always the one that's 1 less than the next power of 2. Does everybody see that? That's why this is 2 to the power of k minus 1. It's 1 less than the next power of 2 in the denominator. So all I do, this is the general recipe. All I do is I replace all these terms with the first term. 1 over 2 to the power of k minus 1 plus... Wait, I'm missing some dots. Let's put some dots in. Because there isn't just those 3 terms, right? Sorry, 4 terms. There's several terms in between here. There might be many terms. 1 over 2 to the power of k minus 1, and so on, plus 1 over 2 to the power of k minus 1. So I have all of these terms here. Do you see a term that's missing on the furthest right here? So I have 2 to the power of k. Whoops, 2 to the power. Yeah, 2 to the power. Now keep in mind, this is 2 to the power k minus 1, not the exponent. The exponent doesn't have minus 1 in it. It's 2 to the power k minus 1. Do you see that there's a term that's missing in this series? It's this one, this final one. You'd agree with me if I just append that onto the end. I end up with 1 over 2 to the power of k, which you'd agree is less than or equal to 1 over 2 to the power of k. So this right here is this finite sum right here. So this is the first series. This is the second series. Do you see how using the same strategy I showed you at the beginning of this with the bucketing, where I sum over the inequalities, I can get now a nice clean argument that says that everything on the right hand side now, if I added up all of these terms, these all have to be greater than or equal to everything that I add up on that side. So that brings me to the following. So let me summarize this, and you'll see quite quickly what we do. So, putting it all together. Now remember, we want to have something that relates the nth harmonic number to this other series that I bounded it above by taking the next highest power of 2. And then what I did is I created a second series. So I want to sandwich this the one that with the rounded up n, which is m. I want to put that one in between the nth harmonic number and the second series that I've invented from h of 2 to the power k. So h of n is less than or equal to h of 2 to the power k, right? Which this right here, now normally when you write a statement like this, you have to keep in mind what it's saying. So remember, this is still for n is greater or equal to 1. I'm just omitting that because I'm running out of space, but you would want to include that. So I have this, and now this is the second series. So I have 1 plus 1/2 plus 1/2. Now this is the trick. Okay. So remember, in the second series, I write out the fraction where the power of 2 appears in the denominator that number of times. So 1/2 appears twice because the denominator is 2. So it appears twice. 1/4 appears 4 times because there's 4 in the denominator. I would have 8, the same idea, and so on and so on. So then I would have 1/2 to the power of k minus 1 plus a whole bunch of 1/2 to the power of k minus 1s. And then I would have one final term, which is 1/2 to the power of k. What can you say about this, or this, or this? Well, this is equal to 1. So if I sum up those terms, they equal 1. And when I sum up all these terms, I end up with 1. Is that interesting? So now I have a whole bunch of 1s I'm adding, plus a 1/2 to the power of k. How many 1s are there? Well, this 1 appears here because it would have been 2 to the power of 0, which is equal to 1 in the denominator, right? So you would have how many 1s? Well, there's the exponent here is k minus 1 plus this extra 1, which is k. So this is k plus 1/2 to the power of k. Let me just get rid of that extra there. So it's k plus 1/2 to the power of k. Now, I just want to unfold some notation that was for my own convenience. Recall that k is equal to the ceiling of log base 2 of n, remember? And n is less than or equal to m. And what was m? That's 2 to the power of k. So just remember this. This is important. This is just to make things a little easier when we wrote down some of the things we did for our second series. Now this is where we make our observation. Observe that for all n greater or equal to 1, that h of n is less than or equal, because remember, that's what it says up here. I'm just going to get rid of the middle. So I'm just getting rid of all this, because now I know that h of n is less than or equal to this term, these two terms, less than or equal to k plus 1/2 to the power of k, which, what's k, remember? It's the ceiling of log base 2 of n. Log base 2 of n. But what's 2 to the power of k? That's m, right? So that's 1/m. But if I have a denominator that's 1/m, and I know that n is less than or equal to m, would you agree with me that if I want something that's slightly bigger than this, if I replace m with n, I should end up with something larger? Just like if I had 1/4 and I replace it with 1/2, you'd agree with me that the 1/4 is now less than 1/2, right? Because now my chunk is bigger, because the number is smaller in the denominator. So all I'm going to do is just make that small substitution. So I'm going to replace 1/m with 1/n, plus I'm going to do the following little trick. Now, one known fact about the ceiling function, when I take a number like this in the logarithm and I round it up, it'll go up to the next nearest integer, right? So what if I just take this, because keep in mind, this could actually be a power of 2 and it will actually be an integer, but sometimes it isn't. But it might be it'll be either between the number rounded down to the lowest, the next lowest power of 2, or it'll be one higher. So what does that mean? That means if I just add 1 to this result without the ceiling, I'll get an upper bound on this right here. Why? Because whenever I round up a result, it can never be more than the whole amount or unit. And in our case, in the ceiling, it's a unit of 1, because I'm rounding up to the next integer. What's the next integer? Well, it's that integer plus 1. So this would just be log base 2 of n without the ceiling plus 1. So it's log base 2 of n plus 1, but plus 1's not a part of the logarithm. Plus the 1 over n. But you would agree with me that 1 over n is always going to be less than or equal to 1, right? Because when n is equal to 1, it's 1. When it's equal to 2, it's 1/2, so on. So I'm just going to make this simpler for myself. So I end up with log base 2 of n plus 1, which is equal to log base 2 of n plus 2. So now I have log base 2 of n plus 2. Now look at this. I have something that relates to logs. Look at that. Isn't that interesting? Man, no, we're doing good. We're just about done, believe it or not. We got all of the really nasty stuff out of the way. So now what I'm going to do is I'm going to invoke the first strategy I told you. I told you it was all going to come back together. What I want to do is I want to make the logarithm, because remember, I want to show that the nth harmonic number is big O of log n. So I want to make this look like something that is a logarithmic term times some constant. Well, I have something that looks kind of like that, right? Maybe if I can pick an appropriate c and an appropriate n0, I can turn that 2 into something that looks like a log. That's going to be, it's not as straightforward as before, but it's the same idea, I assure you. So I'm going to pick c is equal to 2, and you're going to see why. Oftentimes when you're doing these types of proofs, you would normally try to figure out what c and n0 are first, and then you would try writing it out yourself. Unless you're really that certain. Then we need to find n0 so that h of n is less than or equal to 2 times log base 2 of n. So now h of n, we know that h of n is less than or equal to log base 2 of n plus 2, right? I'm going to pick n0. I'm going to try to determine an appropriate n0 so that I can turn this 2 into something that looks kind of like this. And I bound it properly. Just watch this. I promise this is going to be kind of slick. Notice that when n is greater or equal to 4, we get the following relationship that's going to happen. Now you might ask, why 4? Okay, well, what's log base 2 of 4? Well, 2 squared equals 4, right? So I want to get something that makes it look like a log, like I want to make it something that outputs for a logarithmic function that has base 2. I want to make it output 2, at least. So I'm going to assume that n is greater or equal to 4. So I want you to notice that h of n is going to indeed be less than or equal to log base 2 of n plus 2, which is going to be less than or equal to log base 2 of n plus log base 2 of n. Now, as I said, we know that this is going to be at least 2 because log base 2 of 4 is equal to 2, right? And one fact I didn't bring up here, but it might be worthwhile mentioning if you know a little bit about calculus, is that the logarithm is technically, it's an increasing function. So, you know, it's not going to like dip down all of a sudden. Why? Because remember, if you increase the power of an exponent, the output gets bigger, right? That's why. I'm not going to worry too much about that. So, let's do this. But what's this? What's this? Well, that's just 2 times log base 2 of n, right? So I'm just going to choose n0 is equal to 4, right? Because I've done what I need to show. I show that h of n is less than or equal to 2 times log base 2 of n. Do you see how now this is an example where n0 is not just 1? Okay, so we choose that. Now we just conclude. Therefore, by the definition of big O, I'm running out of space down here. By the definition of big O, h of n, or the nth harmonic number, is big O of log base 2 of n, and we're done. The proof is finished. We're all good to go. And we're done. Now, at first, this looks really daunting. The big intuition here is getting that second series and knowing how to bound the nth harmonic number. Like I said, there is an alternative proof that if you assume that n is a power of 2, that you get right away h of 2 to the power of k, and you can write out the second series. But I felt like I would give you a little bit more of a general proof, so it works for any n, and I don't require a notion called smoothness. So with that being said, that wraps up the example, and now you know that if you ever encounter a harmonic series, like a particular finite one, harmonic series pop up in all sorts of neat applications, but I can't talk about them really here. But you know it actually has a logarithmic asymptotic behavior, which is very interesting. So, that being said, that concludes this example. Okay, I think that's all my examples. I'm going to put my hat on for dramatic purposes. Anyways, guys, I'm going to let you go. I'm going to magically walk that direction, and then I'll come back and turn off the stream. So I'll say thank you very much. I don't see any questions right now. Let me just check one more place just to make sure there's nothing else. Okay, I don't see anybody else that's asking questions. I think we're good to go. Anyways, I'll say thank you very much, and have yourself a beautiful day. I'm back. I'll see you later. You have yourself a beautiful day. I'll have a February update sometime very soon, okay? So, I'll have yourself a beautiful day. I'll see you later.